Hello everyone. Today in this class we will discuss about Rolle's theorem and mean value theorems. First we will discuss about Rolle's theorems. So let's start. Rolle's theorem. Let f be a real function defined on closed interval a comma b such that number 1 f is continuous on the interval closed interval AB. Number 2, f is differentiable on the interval open interval AB, A comma B. Next, number 3, f of A is equal to f of B. Then there exists a real number C belongs to open interval A comma B such that f dash C is equal to 0. Remember, if f be a real function defined on closed interval a comma b such that f is continuous on the interval closed interval a comma b, and number 2, f is differentiable on the open interval a comma b, and number 3, f of a equal to f of b, then there exists a real number c belongs to open interval a comma b such that f dash c equal to 0. This is called Rolle's theorems. Now we will take an example related to Rolle's theorem. Exercise 5.1, question number 1. Verify Rolle's theorem for a function. Verify Rolle's theorem for a function f of x is equal to x square minus 2x minus 8, comma x belongs to closed interval minus 4 comma minus 2. We know that if f is a real function, then number 1, f is continuous on open interval a comma b. Number 2, f is differentiable open interval a comma b, and number 3, f of a is equal to f of b, and then there exists a real number c belongs to closed interval a comma b. Then f dash c equal to 0. Remember these points. Solutions. Here f of x, this equal to x square minus x square x square plus 2x here f of x is equal to x square plus 2x minus 8 comma x belongs to close interval minus 4 comma 2. Here f of x is equal to x square plus 2x minus 8. Number 1, since this is a polynomial function, we know that polynomial function is continuous at every point on real number is if x belongs to R. Since f of x is a polynomial, so it is continuous in closed interval minus 4 comma 2. The first condition exists. F of x is continuous on closed interval a comma b. Here f of x is equal to x square plus 2x minus 8. Since this function is a polynomial, therefore this function is continuous in closed interval minus 4 comma 2. Number 2, since f of x is a polynomial, so it is differentiable in open interval minus 4 comma 2. We know that if a polynomial function is differentiable, here f of x is equal to x square plus 2x minus 8. Therefore, this function is a polynomial. Therefore, it is differentiable in closed interval, open interval minus 4 comma 2. Number 2 exists. Next, number 3. F of a equal to f of b. Here, a is equal to minus 4. Therefore, we will find f of minus 4. F of minus 4 is equal to minus 4 whole square plus 2 into minus 4 minus 8. This equal to 16 minus 8 minus 8. 16 minus 16, this equal to 0. Next, f of b. Here b is equal to 2. Therefore, f of 2 is equal to 2 square plus 2 into 2 minus 8. This equal to 4 plus 4 minus 8. 8 minus 8. This equal to 0. Therefore, f of b is equal to f of a. F of minus 4 is equal to f of 2. Our third condition is exist. F of is a polynomial, therefore it is continuous on closed interval minus 4 comma 2. F of x is polynomial, therefore it is differentiable on open interval minus 4 comma 2. And also number 3, f of minus 4 is equal to f of 2. So there exists a number c so there exists a real number c belongs to minus open interval minus 4 comma 2 such that f dash c this equal to 0 implies here f of x is equal to x square plus 2x minus 8. Therefore f dash x that means derivative of f of x this equal to 2x plus 2. Therefore f dash c equal to 2c plus 2. That implies f dash c equal to 2c plus 2 is equal to 2. Therefore 2c equal to minus 2. Therefore c equal to minus 2 divided by 2. This equal to minus 1, which is belongs to open interval minus 4 comma 2. Therefore thus Rolle's theorem is verified. Thus Rolle's theorem is verified because the first condition exists. Here f of x is a polynomial, therefore it is continuous on open interval, closed interval a comma b. Second condition is exists, since f of x is a polynomial, therefore it is differentiable on open interval minus 4 comma 2. And third condition is exists, f of minus 4 is equal to f of 2. Then so there exists a real number c belongs to minus open interval minus 4 comma 2 and such that f dash c equal to 0. Here f of x is equal to x square plus 2x minus 8. Therefore f dash x is equal to 2x plus 2. Therefore f dash c equal to 2c plus 2. Therefore f dash c, that implies 2c plus 2 is equal to 0. Therefore c is equal to minus 2, which is belongs to open interval minus 4 comma 2. Thus the Rolle's theorem is verified. Mean value theorem. Next we will discuss mean value theorem. Let f be a real function, defined on class interval close interval a comma b such that number 1 f is continuous on the interval close interval a comma b. On the interval close interval a comma b. If f is a real function defined on defined on close interval a comma b such that f is continuous on close interval a comma b. Number 2, f is differentiable on the interval open interval a comma b. Then there exists a real number c belongs to a comma b such that f dash c, this equal to f of b minus f of a divided by b minus a. F be a real function defined on interval close interval a comma b such that f is continuous on the interval close interval a comma b, f is differentiable on the open interval a comma b, then there exists a real number c which is belongs to open interval a comma b such that f dash c equal to f of b minus f of a divided by b minus a. Now we take an example related to mean value theorem. Question number 4, exercise 5.8, question number 4, verify mean value theorem, verify mean value theorem, verify mean value theorem for if f of x is equal to x square minus 4x minus 3 in the interval close interval a comma b, where a is equal to 1 and b is equal to 4. Verify mean value theorem for if f of x is equal to x square minus 4x minus 3 in the interval close interval a comma b, where a is equal to 1 and b is equal to 4. Here f of x is equal to x square minus 4x minus 3, comma x is belongs to where x is belongs to close interval 1 comma 4. Number 1, since this is a polynomial function, therefore this function is continuous on the close interval a comma 4. Since f of x is a polynomial, we know that polynomial function is continuous polynomial, so it is continuous in close interval 1 comma 4. Next, number 2, also we know that polynomial function is also differentiable since f of x is a polynomial, so it is differentiable in open interval 1 comma 4. Next, so there exists a real number, so there exists a real number c belongs to open interval 1 comma 4 such that f dash c is equal to f of b such that f of b minus f of a divided by b minus a. So there exists a real number c belongs to open interval 1 comma 4 such that f dash c equal to f of b minus f of 1 divided by b minus a. That implies f dash c here f of x is equal to x square minus 4x minus 3. Therefore f dash x equal to 2x minus 4. Therefore f dash c is equal to 2c minus 4. Here f dash c is equal to 2c minus 4. 2c minus 4. D is equal to 2c minus 4. F of b, here b is equal to 4. Therefore, f of 4 is equal to 4 square minus 4 into 4 minus 3. D is equal to 16 minus 16 minus 3. D is equal to minus 3. F of 4 equal to minus 3 minus f of a, that means f of 1 d is equal to 1 square minus 4 into 1 minus 3. 1 minus 4 minus 3. D is equal to 1 minus 7. D is equal to minus 6. F of a equal to minus 6. Next, b minus a, 4 minus 1. This implies 2c minus 4. D is equal to minus 3 plus 6 divided by 3. 2c minus 4. D is equal to 3 by 3. 3 by 3. D is equal to 1. 2c. D is equal to 1 plus 4. That is equal to 5. Therefore, c equal to 5 by 2. Which belongs to of an interval 1 comma 4. Here c equal to 5 by 2. Here c equal to 5 by 2, which belongs to 1 comma 4. That thus the mean value theorem is verified. Here c belongs to 5 by 2, which here c is equal to 5 by 2, which belongs to of an interval 1 comma 4. Therefore, mean value theorem is verified. This is the answer. Next, we will discuss miscellaneous exercise, chapter number 5. Chapter 5. Chapter 5. Miscellaneous exercise, chapter number 5. Question number 1. 3x square minus 9x plus 5 whole to the power and differentiate with respect to x. Differentiate with respect to x. Question number 1. 3x square minus 9x plus 5 whole to the power 9. Solutions. Let y is equal to 3x square minus 9x plus 5 whole to the power 9. Find the differentiate with respect to x. Given 3x square minus 9x plus 5 whole to the power 9. Let y is equal to this. Now, differentiating both sides with respect to x, then we have dy by dx. D is equal to d by dx 3x square minus 9x plus 5 whole to the power 9. This is equal to, we know that d by dx f of x whole to the power n. We know that d by dx f of x whole to the power n, d is equal to n into f of x whole to the power n minus 1 into d by dx f of x. Already we have learned d by dx f of x whole to the power n is equal to n into f of x whole to the power n minus 1 into d by dx f of x. Here f of x is equal to 3x square minus 9x plus 5 and n is equal to 9. Here f of x is equal to 3x square minus 9x plus 5 and n is equal to 9. Then we have n into n, here n is equal to 9, n into f of x. F of x is equal to 3x square minus 9x plus 5 whole to the power n minus 1, that means 9 minus 1 into d by dx f of x, 3x square minus 9x plus 5. This is equal to 9 into 3x square minus 9x plus 5 whole to the power 8 into d by dx 3x square minus 9x plus 5. This is equal to d by dx 3x square minus d by dx 9x plus d by dx 5. This is equal to 9 into 3x square minus 9x plus 5 whole to the power 8 into 3 into d by dx x square minus 9 into d by dx x plus d by dx 5. Here 5 is a constant, therefore we know that derivative of d by dx of constant, this equal to 0. This equal to 9 into 3x square minus 9x plus 5 whole to the power 8 into 3. d by dx x square, d by dx x square is equal to 2x, equal to 2x minus 9 into d by dx x, d by dx x is equal to 1. This is equal to 9 into 3x square minus 9x plus 5 whole to the power 8 into 3 to the 6, 6x minus 9. Taking common 3, then we have 9 3 the 27 into 3x square minus 9x plus 5 whole to the power 8 into 2x minus 3. This is the required answer. Thank you.